Hello, my name is Carl Cook, and I'm President and Chief Technical Officer of IntelliDynamics, a division of Biocomp Systems. And this is session 3 on causality. And we'll move on to our little pyramid here, where we do top-down planning to identify the business opportunity, and then a bottom-up building of the solution. And in this video, we're going to talk about causality. By this point, you have accessible data. Through the data virtualization, you really don't care where it is, which is rather convenient. And you have cleaned, validated, and your data and is converted into a suitable format for analysis. The causality part of it is where you are exploring your data, trying to understand the cause and effect relationships that are within it. You can skip this step if you just want to build models and put them online and make estimates of something. However, it is useful to understand your data and what it's trying to tell you. And especially if you're going to go all the way up to optimization, if you're not just making estimates in real time, but if you want to do real-time closed-loop control, it's best to understand the data fairly well so that you can build models that are intuitive and have the proper responses to things that you change. And so the causality part of it is probably the most challenging and most useful, and probably the most artful. So if we want to understand the result A that we're after, we need to know what causes A. And as I said, this is the hardest part because there's a lot of, well, I would call them tricks that are played, and there's lots of complexity that may be involved in things that cause A and their impact on it. And you need to be open-minded that as a general rule of thumb, that rules of thumb are wrong or conditional about half the time. So over the last 20, 30 years that we've been doing a data analysis, people will say, well, this result is driven by this variable and it should have a positive correlation. And then we get into the analysis of it, and then maybe they give us a list of 10 of those rules, and we get into the analysis of it, and a few of them they're just not supported by the data. And another chunk of them are, yes, it's true, but it's only true under these conditions. And yes, those conditions are the most frequent, but there are exceptions where that rule actually reverses. Also, we must be mindful that correlation is not causation. Just because A jiggles around a certain way, that variable B jiggling around a certain way does not mean that A causes B. And that time is truth. That if you take a look at the time events of what happens, we know that an effect cannot come before a cause. Yeah. There are loops, however, but generally speaking, if you unwind time and lay it flat out on a table, if that's possible, and it is, you will see that a cause must come before an effect. And so that helps us understand what truth is. Also, we must realize that life is nonlinear, that you just generally don't draw a straight line between A and B, that causes can be nonlinear. They may have diminishing effects after you get above a certain level. They may have irregular shapes to them, to where under let's say in oil and gas, if you're doing lift gas injection, the more gas you inject into the well to lift the oil out of it, the more oil production you have, right? Wrong. Because you can go and then you can inject too much, and then you actually, the more gas that you apply, the less injection that you have, or less production that you have, and you actually have a inverted parabola type of curve. And so you want to stay over on one side of the curve, and so life is nonlinear. And there are things such as circular causality, that A causes B, and then because of B, something happens to cause A to change, which causes B to change, which causes A to change. And then you can get into chaotic systems. And sometimes a human is in that loop. And causes are not necessarily direct, that A causes B, and B causes C. Therefore, A causes C indirectly through B. And you may need an iterative approach, that you may go take a look at things, you may take certain actions, you may get effects that you don't anticipate. You go back, you take a look at, with fresh eyes, take a look at the data, go like, ah, yes, okay. During these conditions, this happens, and those conditions, that happens. And causality can only be proven by direct manipulation. You cannot really look at data and afford any proof. You have to go back and change A and observe B changing according to your prediction of how it would change. And that's the only way. And you might have to do that a few times to prove it. Okay. So there's a number of available technologies within intellect architecture to support this type of activity. One is data visualization. So you can have trend plots, scatter plots, that's A versus B on a scatter plot, histograms, also time-based correlations, causal maps, modeling with input variable sensitivities. So you actually build a multi-dimensional model and take a look at how the rate of change of the result is impacted by each of the changes of the inputs to the model. And the modeling also takes out noise. And also multidimensional response curves and surfaces. So the various methods you can use, as I mentioned before, I know, that is saying that you know for a fact that A causes B. You have to be very careful. You may be quite correct based on your experience. But just taking a look at physics, for example, is often a simplification of what actually happens. I mean, if you take a look at the formula for water flowing from the water pipe into your house, that formula is huge. Look up in Wikipedia, Navier-Stokes equation, and you will go, oh my God, how can I even figure out how my toilet flushes? Well, nobody knows how your toilet flushes. The swirling is something that's indescribable, but it's known well enough to be able to be used for a benefit. So that's really what we're after, is knowing enough to be used as a benefit. And the preconceived notions that you may have, you need to be careful. Even Einstein proved that Newton's laws are correct under common conditions, and under other conditions they come apart. So even following the laws of physics and first principles is something to be not to be heavily relied upon, but as a guiding starting point. And as I mentioned before, rules of thumb are about 50% correct. The whole part of the causality analysis and the artfulness of this is that you really need to become one with your data. You need to get exposed to it, to see it and view it and explore it and get into it so that you really understand what your data is telling you. And one way is to look at scatter charts. At the upper right, we see a one scatter chart between two variables. Let's say these are actual process operations. The bottom is temperature and the vertical is the desired result. And we can see that temperature has very little effect until it gets above about 130 on the horizontal axis, and then it starts kicking in. That's useful information. You also see various exceptions. The middle scatter chart on the right, halfway down, is another process operation, which is a valve opening across the horizontal axis and flow on the vertical axis. And we can see that below about 60% valve open, we have a significant relationship between opening the valve and liquid flowing. But above 60%, that is to say that it's open more than 60%, we can see that that relation stops. That the valve is open enough that opening it more makes very little difference. So you can't just say, oh, opening the valve causes more flow. Yes, it causes more flow if the valve is already opened less than 60%. If it's open more than 60%, no, opening the valve really does not cause more flow. Maybe a little bit, but within the noise, you're probably not going to see any. Another aspect is unwinding time, which I'll talk about in a moment. I have more on that. And evaluate model sensitivity and create a theory and test it by manipulating the process. Also, part of the exploring your data has to do with the trend plots and the histograms at the bottom. The trend plots can give you a feel for the data, that there's certain heartbeats in some of the variables that may or may not be correlated with other variables. Other variables dance together on the dance floor of data. In the histogram, you can see that, oh, my process is generally operating there around the center, but I also see that I'm operating at the extremes fairly frequently. Well, that's useful information, especially if you know that if one of those has to do with valve opening and you're operating substantially at an extreme, that you're not going to get much effect on flow, for example. So you can take these different learnings and perspectives and combine them together to improve your experience and understanding of your data. I mentioned that I had more on unwinding time. And I said earlier that causes must be before effects. And so you can do a sliding time window correlation. That's the most simplistic method, but it does work in most cases. And you can see various bumps in the correlations where A leads B. And in the chart at the top, I also have another bump where B leads A. So A causes B and then B causes A. A causes B more strongly because the correlation is higher than B leading A. And this is actually a case where A is temperature and B is a result, and A is known to cause the result, and so that's that bump that we see. And there's about a 20-minute delay between changing A and B changing. But the other bump on the right-hand side of that chart is where the result is causing the cause to change. Now what's this? Well, that's the operator of the process observing B and changing A. So there's a human in the loop, there's a closed loop going on here, which can lead to a chaotic system if it's not properly damped. And the temperature is causing B the result. The operator sees B the result and changes the temperature set point, which causes the temperature to change. So you end up with a loop. That's very common. So when you're looking at B, the result, you have to take a look at both the temperature and what the operator is doing, reacting to B and changing the temperature. The next chart is a causal map. It's a little old. We're going to invest into improving the technology now that it's fairly proven. But basically, the vertical axis is the causal strength. Positive is top, and negative is at the bottom. Negative correlation or effect. It's not just correlation. And then the horizontal axis is the time lag, where the objective that we want is on the far right, where everything points to it. And so we can see that certain variables affect the objective at different times to different degrees. That's very useful. And it also tells us that in this case, in the lower part of that chart, center right, you'll see tower temp. If your YouTube pixel density is high enough, HD, is it the red item with the red dot on it is tower temperature. That's something that we control. We also know that if we change tower temperature, and by controlling that, anything that comes between tower temperature and the result that we cannot control, we are a victim of. That is, once we set tower temperature, say 10-15 minutes later, we're going to get a result, and that's going to be based on other factors that we have not been able to foresee because they react faster. Also, to the left of tower temperature are things that we can foresee beforehand and actually adjust the tower temperature, compensating for tower pressure, reboiler return temperature, the feed rate, the feed flow, etc. So this is an extremely useful diagram for understanding cause and effect and what's in your control and what you may be a victim of, and what's not in your control, and something that you can compensate for if it has a greater time lag. So this is a very useful tool. You can apply these lags and model the data and see how well your models work. Another way to view things is to build models and do sensitivity analysis, and we're tooting our own horn here. We're experts in sensitivity analysis because we've done it in so many different markets over so many decades that there's lots of different ways of doing it, and some of them are better than others, and some are very quick to compute. Some things take a lot of time to compute. But the world's multi-dimensional. That is, you cannot just look at A causing B. If C, D, E, F, G also impact B, you cannot look at just one at a time because they may be interacting with each other. So A, B, C, and D through time may be causing an effect on E through time. And so you must look at things from a multi-dimensional perspective. And that's exactly what our modeling technology does. It takes all these different dimensional inputs, A, B, C, and D, and it estimates E, the effect. And then you can go in and take a look at multi-dimensional response curves and surfaces and understand the effect of, okay, given that A, let's look at the effect of A and B together while holding C and D at existing process conditions or at their midpoints or whatever. And then we can see, okay, this is how A and B interact to impact E, the result that we're after. And so we have various ways of doing it. One is the response curves and surfaces. Another one is in the lower left, which shows a green circle around input sensitivity, which is the partial derivative of the output, the effect, with respect to each input. And then that's normalized, and so that everything comes out and sums up to 1.0, which gives you then a fractional value, and that we can see that temperature T1 at a 13-minute lag has the strongest negative effect on the result, which is correct in this case. It has to do with a distillation column type of thing. And we can also see that what the top 3 or 4 variables are that are impacting the result when considering a multidimensional response model. So that's something that's very useful. So in summary, you need to become one with your data and really get in there and understand what your data is telling you. You can use visualization, you can use time analytics, you can look at model sensitivity and multidimensional effects and responses, and then you can come up with a theory that says, if I make these changes, I should get this result, and then test it if you can. I realize that a lot of processes it may not be possible to to change things. You also may learn that you don't have a set point for something that is critical to the results that you're getting. Which then you may go like, I need to control this, and I don't have a means to. And go and start, a control project that says I'm going to come in with a way to do that. And if you don't necessarily have the means to do that, then you might be able to use a model predictive control type of system. Or if you're trying to control product quality, for example, let's say cookie softness, and you have oven temperature and how much, this ingredient versus that ingredient, who the vendor of the ingredient is, etc. And you want to control cookie softness because you want your cookies to be consistently nice and soft for the customer. You can't write an equation for cookie softness. And so you can use our modeling technology to correlate how you're making your product with cookie softness or whatever other result. Might be toilet paper softness or strength. Might be wet tear strength of paper towels. It might be whatever. There's a lot of things you cannot write an equation for. So thank you for your time. I appreciate it. This is the causality aspect of it. It's a lot of art. Requires time and investment. You need to climb inside your data and explore it. And then in the next video, we'll talk about how do you build those models, multidimensional predictive models, and what they tell you, and then how to put those online to make estimates either in real time or on historical data. Again, thank you for your time. I appreciate it, and please stay tuned for a coming video.